Hi. So, if you've been following along with the videos, we discussed the theory of TCPs, the theory of planes, variable waypoints, and how to move the robot relative to the base, the tool, or any plane. So now we're going to put that all together into this concept of a scalable program. And you're going to see how by changing small parameters, we're going to be able to modify the execution of the program and really be able to draw squares in this example all over our plane. So we're assuming two things right now, that we have a plane defined as it is shown here at the origin, like basically where the tip is right now. And we have a TCP that is aligned in that same way. So if we want to draw a square, what are the parameters that we need to draw a square? Or in this case, a rectangle, let's say. So we need a length, we need a width, and we need, if you look at the program here, we have a length of 50 millimeters, we have a width of 50 millimeters. Then we may want to specify at what height do we want to trace this square, right? And finally, we may want to say, how are we going to approach this square? So I want to show you, the first thing is that the basics. So I've defined four variable waypoints, right, as variables. So these P1, P2, P3, P4. So P1 is at 0, 0 and at the dispense height. So that's going to be the bottom left corner of this square. Then P2 is at a length of 0 in the x direction and the length in the y direction. So that is going to travel to that top left corner. Then P3 is going to be the top right corner with a length and a width. And then finally, P4 is going to be the bottom right. And then we would go back to P1. So if you look at this, right, we are going to have P1. We're going to do a linear move to P1, right? And so if I go here and I move up relative to the base, I'm going to move up our dispenser. So we're going to do a linear move to P1. Then we're going to do a process move, right? So linear move to P1. It has sketch rotation as a feature because we're going to want to do it in this plane. Then we are going to go to, we're going to do a move P, again, with a blending radius of 1 millimeter and a tool speed of 20 millimeters per second. And we're going to do that relative to the sketch rotation. And then finally, we're going to stop with a stop L script command, because otherwise a process move will have this sort of rough stop at the end, because it's not a controlled deceleration like a move L. So let's run this and see what we get. So we run it. So we notice, okay, it's properly drawing a square, right? But it's doing it at the origin of our plane. Okay, so we have two things to correct, and we also will probably want to move away from that corner. So the first thing we're going to do is we're going to change these approach points to come in and then come out at a certain height. Okay, so how would we do that? We're going to define a approach, right, which will have a 25 millimeter offset in the C direction. So we're going to define this variable APR, like this. So here our length, our width, our dispense height, and our 4 points. Okay, so now what we can do is we can say, we don't want to start at P1, but we want to translate P1 by that approach point. So we can define another variable, unsuppress this, and call it start pose trans P1 APR. And what that will do is that it will transpose our point P1 by that approach point. So here, rather than moving to P1, we're going to want to move to this new variable called start. Okay, so now, and then when we get to the end, right? When we get to the end, we could go back to that same variable, right, start. But I'm going to show you actually a bit of a better way, which will be that we unsuppress this and we do a move P, right? And we do this move P, and we're going to move to the variable waypoint APR. So that will be an offset of 25 in the Z direction, but we're going to do it relative to the tool, right? And this is, so here we're going to increment up from that point, right? So this is where it's critical, to watch the other videos where I describe, how these move P's work relative to the tool, the base, or the planes. That's why understanding this post trans and post inverse and all of these things matter. And even if you don't get the concept completely, I want to show you the power so that at least it motivates you to go back and sort of understand those functions. Okay, so now we have done that. So now I'm going to play. So you'll see that now I start with an approach, right? I'm doing the same, square. And then at the end, it's actually going to come up, right? And so that is the typical sort of movement that you will have in a dispensing or really in most path finishing projects, right? Or path following projects. You're going to have an approach, do your process move, and then have an approach with which you retract. All right, but now, I said, okay, we wanted to do the square, this blue square here. So really what I would love to do is I would love to offset all of those movements by that amount. And so, well, how do you do that? If you notice here, right, I can't change my feature to be a variable. I can only choose planes here. So this is one trick that I learned to do, is that you can come here to the installation and you can come here to your features and you will have a plane, right, called work plane. And if you edit this plane, it's all zeros, right? So if we were defining it, so you could say plane, and now you don't even want to teach this plane, so it's in yellow, but if I say edit and okay, that becomes a valid plane that is essentially the equivalent of my base. But I will show you how we're going to use that to our advantage. So when we go back here to the program, right, I'm going to say that, and I call usually that plane work plane. So I'm going to say that my work plane is actually so if you look at this function, that my work plane is actually my sketch plane offset by 25 millimeters and 25 millimeters in the X and the Y. And that is, the 25 millimeters and 25 millimeters that is going to correspond to that bottom left corner. And so now, once I have this work plane, I can change my moves to be relative to that work plane. This one and this one relative to this work plane. So now those two moves are going to be relative to that work plane. And so now when I run this, notice that I didn't have to change anything besides that work plane offset. And I am now moving on that square here, right? And, this is really extremely powerful, because if I want to get to that other corner here, well, all it takes is for me to make this 100, sorry, not on the Y, but on the X. We're going to make this 100 millimeters. And we can say play. And now it's going to do my other square. So with just one small change of one number, I'm able to completely offset that whole program, right? And keep all the other parameters. And this is going to be really nice because the actual, another thing that you can do is you can say, well, I actually want to do those two one after the other. Okay, so how would we do that? Well, you can go in here and say loop, right? you have a loop variable called loop1. So how many squares do you want to do? We want to do 2 squares. Okay, so we're going to run this loop twice. So loop x times, we're going to do it twice. And now we're going to move this instruction here inside of here. And we're going to move our square here, cut. And we're going to move that inside of here. All right, perfect. So what does our sketch offset need to be? Well, we know that the first time we want to do it with 25 millimeters, but we know that after that we need to offset 75 millimeters. So we can say plus here, and then we can say variable loop1, right? And then we can say times 75 millimeters. And so what that will do is that it will run the first time, the first time that we come around, loop1 is going to be 0, right? So essentially this will be just 25. But when loop is equal to 1, it's going to be 25 plus 75, and that will give us the 100 for that offset. So now, without, really just changing more than one instruction and adding a loop, if we hit play now, right, we're going to come to this first one. And then after that, so we're going to come up. And now we're going to move over to the second one. And we're going to be doing those. And if we had an array or whatever it was, that's, we could add another loop and we could have an X and Y array, or if we had it all in a line. So that is, there's a lot of wizards that help you do these things. But I think that if you truly understand variable waypoints, you can do all of this very simply yourself. So the other reason why I say that this is scalable, right, is that, if I say, oh, you know what, those 2 squares have changed in size, and now, there are 25 millimeters wide, so something changed in your program or in the parts that you're working with, and now these are 25 millimeters. And I want to do this at a dispense height of 10 millimeters for whatever reason. So when you run this again, right, we're going to come down, we're going to be now at 10 millimeters. And now we're going to be doing these little, half squares here. And we were able to change. I mean, imagine all the waypoints you would have had to change to make that happen if you had written your program in the traditional way of defining waypoints. All right, so that covers, scalable programs using variable waypoints.